Okay, so in this class we're going to yet again have a look at transformations. Oddly enough, that's just sort of how the syllabus turned out. But okay, so transformations, top to bottom. What are we doing here? Well, fundamentally, all we're ever really doing is figuring out how to get from one set of xy coordinates to another set of xy coordinates. Usually that means taking a full function and shifting that in some way, shape, or form. So, how does that all work? Well, fundamentally, as I mentioned, we're just going from one point to another point. And so it doesn't really matter what your function is, as long as you follow these three steps, you'll be able to apply any transformation to any function that you like. And that starts by figuring out what is your transformation. From there, you want to rearrange to get back in terms of the original point, and then sub that original x comma y into your function, whatever that function is. So let's have a look at a few typical transformations, starting with dilations, right? Dilations are all about stretching a function, and mathematically speaking, these are observed by a multiplication on your x value or on your y value, depending on what you specifically want to dilate. In this case, we're looking at dilations along the y-axis. Now, a lot of the time you'll see this written as from the x-axis. These mean the same thing. So just to explain the terminology real quick, if I have some point on an axis like this, I can stretch along the y-axis, which means I'm stretching in this direction, it's going along the y, or I can go away from the x-axis. So here's our x-axis and we're going away from it. Those two arrows are pointing in the same direction, hence they mean the same thing. Now, most of the books are going to talk about from the x-axis, so that's typically what you'll be interested in. Anyway, if it's going from the x-axis, then we're going in the y direction. Hence, our multiplication factor is going to be affecting the y value in this circumstance. So, step one, what does that actually look like? Well, we need to figure out where are we starting and where are we going. Well, we're starting at xy and we're trying to get to xay. And so our new point, x prime, is going to be the old point, x. Nothing's actually changed. X prime equals x. And then our new y value, y prime, needs to be a times y. So a times the original of our y value. From there, next step, nice and simple. This will only ever really be like a linear type thing, where you just rearranging to get x and y on its own. It'll never be any more complicated than linear. So rearranging just by dividing both sides by a in this case. This one doesn't really need to be changed at all. Then from there, once you have that rearrangement, you sub in that new x and y into whatever your function is. So in this case, the x hasn't changed, so x is going to remain x, and the y has changed. So y is now going to become y divided by a. You'll notice that we dropped off the prime notations. That's simply because they were there for us to keep track of which variable is which. They don't actually belong in a function. It was purely just to make sure that we didn't get things back to front. But okay, now that we have that, there's only one step left, which is to get y back on its own. Whenever we write our functions, we usually only ever have y on its own and everything else to the right of the y. That's why we're going to do a further multiplication of a to make sure everything gets on that other side. This bit here is all about what this actually looks like. So if these little vertical bars here mean magnitude. If the magnitude of your a is greater than 1, then the function is going to stretch. It's going to get further along the y-axis. Now, the reason I say magnitude is because it could be either positive or negative, right? Positive 2 or negative 2 still means that you're stretching along the y-axis, whether it be in the positive or negative direction. It just means you're getting further along that direction. But if your a value is between 0 and 1, you actually got to shrink along that direction. So if your point was, let's say, we get another axis, if your point was here and your a was between 0 and 1, then it's actually going to go down a little bit here. It's going to shrink. Okay, that's that. Now we look at how this applies to an actual function. So let's say we have the graph of root x, and we want to do a dilation factor of 2 from the x. Well, for that, we've got to identify, firstly, what is the transformation? Well, dilation factor of 2 from the x means that it affects the y, right? It's going along the y-axis, or in that direction. And since our dilation factor is 2, we're multiplying by 2. That's going to give us our equation, which we then rearrange to get x and y back on its own. And then finally, we sub that into the actual function. So that means x is going to stay the same once again, and y is going to become y divided by 2. Finally, multiply both sides by 2, and that applies the transformation. Now, you don't strictly need to follow these steps to do basic transformations like this. If you do know what a dilation factor of 2 from the x means, then you can very quickly look at this and just realize, oh, all I've got to do is multiply my function by a. The reason why I'm teaching these steps at all is because it will help when you have to do multiple transformations at the same, well, I should say multiple transformations in sequence, which is what this is building up to. But okay, before that, let's look at the fundamentals of transformations. So, another set of dilations here. In this case, we are doing a dilation along the x, or alternatively from the y. Those mean the same thing. Again, along the x, so here's our x-axis going in that direction. Alternatively, from the y, getting away from our y values. Those are pointing, once again, in the same direction. So, not much is changing here. The a value is now going to go on the x this time. Rearrange, substitute. That's all it really takes. Now, one key thing worth mentioning here is that there is no further rearranging to be done for this, because the y is already on its own. And so what you'll find is that whenever you apply a dilation factor from the y, or along the x, it looks like a division when it gets subbed into a function. Versus if you compare that to this dilation along the y, or from the x, it looks like a multiplication. Hopefully this sheds a bit of light as to why it looks the way it looks. In this circumstance, we needed to get y on its own because that's how we write functions. In this circumstance, y is already on its own, so there is no need to move it anywhere. But fundamentally, it's the same thing. If a gets bigger, you stretch. If a gets between 0 and 1, you shrink. Once again, another example. Same factor, but this time it's from the y. So the 2 is going to go on the x, rearrange, substitute, and then that's pretty much all you've got there. Okay, reflections. So the way to think of reflections is to think of the axes of reflection as a mirror. So in this case, we're looking at a reflection in the y-axis. And so if we look at this point that we had earlier, here is our y-axis. A reflection in the y-axis means that the y-axis acts like a mirror. And so you have your little mirror here, and so the reflection of that means your new point would be over here. Now if we compare the location of these 2 points, we'll see that horizontally they haven't changed. They share the same y value. That hasn't changed at all. But what has changed is the x. Right? This is a negative x, this is a positive x. And so whenever you have a reflection in the y-axis, you have to put a negative sign on the x point. Otherwise, everything else is the same. So x dash is now negative x. Rearrange to get back in terms of x and y, and then sub that into your function, whatever that function is. And in this case, it'll look like the negative sign on all of the x's in the function. So if we see how that looks like as an example, you've got f of x becoming some sort of quadratic. A reflection in the y-axis just means that every single x that we see here is going to be replaced with a negative x. So you follow your 2 steps, and then on the 3rd step is when you do that substitution of negative x. Now, this is pretty atypical. It's not common that you'll see a function that looks like this in a so-called untransformed state, or at least not in its general form. So when they're in this form, it can be very hard to figure out what's happened to your function. Like, for example, if you're just comparing 2x squared plus 3 to the result after transformation, if all you did was look at those things, it would be very hard to figure out what was done to it. So that's kind of why we typically don't use that. This is more so just as a proof of concept to say, hey, you can still do this even if it does look a bit weird. reflection in the x-axis, so same deal, but now it's on the y value. So again, if I get up another axis and a point, the x-axis is now our mirror. And so if that's the mirror, then the point is going to shift vertically over to here. Now vertically, these have the same x value, right? Nothing's changed there. But what has changed is the y value has gone from positive to negative. And so that's why the y value gets a negative. Rearrange, substitute, and in this case, we see that reflections in the x-axis look like a negative sign on the entire function. So again, we can see that here. If you already know that little shortcut, then all you have to do is put a negative sign on the front of this whole thing and you get there nice and simple. Or you can follow the 3 steps here that I've outlined and that will still get you there. All you're doing is putting negative y and then rearranging from there. Okay, last up, translations. So the way this one works is that you're shifting a function either horizontally or vertically. So up, down, left, right, any of those. In this case, we are doing horizontal translations to begin with. So fundamentally, all you're ever doing for horizontal translations is either adding or subtracting a value to your x point. So you're starting at some original x point, and if you want to go right, you would add another value to it. Now, I say that, and that should probably ring some alarm bells if you've already seen this concept before, because normally you think, whoop, if I want to go right, I should do x minus a. So what's going on here? Well, hopefully this 3-step process here will shed some light on that. But yes, if you're just looking on a point-by-point basis, then shifting right does in fact mean that you're adding whatever that shift would look like. The reason why it looks different is because when you go through your rearranging, this plus a now looks like a minus a. Because, well, you've gone from x dash equals x plus a, and you've rearranged to get x on its own. Now it looks like a minus. And it's this thing that you sub into your function which finally makes it look like a subtraction, even though under the hood you are actually adding to your x values every time you do that. So how do we actually do it? Well, in this case we have a horizontal translation of -5, and so if you follow the procedure here, it just means that you add a -5, or just subtract 5 from your x, rearrange that to be positive, and then every x that you see in here gets replaced with x plus 5. So instead of saying 2x squared, you say 2 bracket x plus 5 all squared. Instead of saying 3x, you now say 3 bracket x plus 5. Expand, 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 and that gives you a final answer. Vertical translations, again, very common, very similar, where you're adding to your y value. Now, the reason this one still stays as positive is because, again, once you go through your rearranging, you'll notice that you've got y dash equals y plus a. That becomes a minus, but when you put that y minus a on the left, again, we want to make sure that y is the only thing on that left-hand side. And so when you put that to the other side, it now becomes a plus again. That's why plus is up and minus is down. These ones are nice and simple because if you want to shift anything up or down, you literally just add or subtract whatever that coefficient is at the very end. Or if you want to follow a more rigorous procedure, you would say, well, okay, I want to shift down by 2, so I'm going to do a subtraction of 2 on my y, rearrange that to get y on its own, and then replace that y with y plus 2, and then finally put it to the other side. So again, a lot of work, but this will set you up nicely for the next bit, which is how we do things in sequence. So how does that work? Well, why is that important rather? So the reason why sequences are important is because the order in which you do transformations matters a lot. So to highlight this fact, I have 2 sets of different sequences here, each containing the exact same transformations. So they both have a dilation factor of 3 from the x, they both have reflection in the x, and they both have the translations of 5 in the x and 1 in the y. 5 in the x and 1 in the y. But they're written in different orders. And so we've got to see how that actually has a decent impact on what the end result is going to be. As for how we handle this, we're pretty much just redoing step 1 over and over again of the previous situation until we've applied all of our transformations. And it's only then that we follow up with the rearranging for x and y, and then subbing in at the end. So what does that look like? Well, let's have a look at example 1. So that's this situation here. We're starting with a dilation factor of 3 from the x. So nice and simple. It's from the x, means it's going along the y. It's going away from the x. So our multiplication is going to affect the y. Now, here's how it works next. It's followed by a reflection in the x-axis. And so, under those circumstances, what you're going to do is start where you left off, right? You start where you left off. So reflection in the x, again, that means that you have a x-axis acting like the mirror, and so you're going to flip in the y. You're going to flip the y value, so the y value becomes negative. So you're starting at x comma 3y, and you go to x comma negative 3y. Finally, we have translations. So we have 5 in the positive x, 1 in the positive y. So you're going to figure out where you left off from, and then add those at the end. X is now going to become x plus 5, and negative 3y is going to become negative 3y plus 1. So that's the result for the previous thing. If you needed to, you could then sub that into a function. In fact, yeah, might as well do that now. Why not? We can do that by hand. So if you had, yeah, so that was like step, I guess that would have been step 3, right? Just repeatedly do that over and over again. So that gives you x dash is equal to x plus 5, and y dash is equal to negative 3y plus 1. And so all we're doing there is rearranging to get x and y back on their own. Nice and simple. X equals x dash minus 5, y equals, probably should do that in 2 steps there actually. Y dash minus 1 equals negative 3y, and then y equals negative y dash take 1 over 3. And then all we're going to do is have some function, whatever that function is, y equals f of x, replace our y with that, and our x with that. So we're going to have negative bracket y take 1 on 3 equals f of x take 5. And then finally, we're just going to get the y back on its own because that's how we write functions. Multiply both sides by negative 3. Negative 3 f of x take 5. And then add 1 to both sides. Negative 3 f of x take 5 plus 1. That's how it would look in a function, whatever that function is. So just replace f of x with whatever your function happens to be. Okay, example 2. Same transformations in a different order. Now we're starting with the translations. So 5 in the positive x, 1 in the positive y. Okay? Add 5 to x and 1 to y. Nice and simple. Here's where it gets a bit different. When you apply a reflection in the x-axis on this, the negative sign doesn't just go on the y. More specifically, it goes on the y spot. Everything that is in that spot. So you're going to put that negative sign wrapping the entire thing. Same thing can be said for a dilation. Dilation factor of 3 from the x, it's going to affect the entire y spot. Negative, it's going to be a multiplication of 3 on that entire thing. And so if you just directly compare where we started and where we ended, I guess where we ended off on the last one versus this one, you can see that those are different things, right? Expanding this out is just going to be negative 3y minus 3, whereas this one is negative 3y plus 1. And that's it for that. So that's how we apply transformations in general and how we could do a sequence of transformations. Now, the next logical step to look at would be, well, okay, sure, I get how we apply transformations, but how do I figure out what was done in reverse? Like, how do I look at a transform function and figure out what was done to it? Or even better, how do I figure out what it would take to go from one to another? That's what this is all about. So we follow these 4 steps here. Again, looks like a lot, but you'll find that it's kind of similar to what we just looked at. So starting off with step 1 here, we've got to figure out what is our original function and what is the new function. So basically, where are we starting and where are we going? In this example here, we are starting at f of x and we're going to g of x. So that's the kind of wording you might expect. Find a sequence of transformations which maps a function f to the function g, going from f to g. So we're starting at f, going to g. Now why does that matter? Well, as far as notation goes, it means that we're going to give xy to where we're starting, and we're going to give x dash y dash to where we're going. That's going to make it easier to keep track of what's what. So instead of saying f of x is equal to that, we're now going to say y is equal to that. And instead of saying g of x is equal to that, we're going to say y dash and x dash for that function. That's a key thing worth mentioning there. So the dashes always go to the function that you're trying to get to. Now, the next thing up, we're going to rearrange all the transformations factors that are affecting the y to the y side. We're going to leave all the x stuff on the x. So what does that actually mean? Well, if we look at our function here, we see a vertical translation of 6 and we see a dilation factor of 3 here. Both of those are affecting the y. And so what we're going to do is rearrange to get all those on the other side. So subtract 6, divide by 3, and sure enough, that's what we get. G of x, or the y dash, has no transformation factors. It is just a generic truncus. And so there's nothing else to be done there. So we're going to be left with this equation, which is our y and x, and this equation, which is our y dash and x dash. Next, what we're going to do is equate the x components to each other and the y components to each other. So this is the y component of the first function, this is the y component of the second function. We're going to create an equation that equates both of those two things together. We're going to do the exact same thing for the x stuff. X take 1 is equal to x dash. From here, we always rearrange for x dash and y dash. The reason being is because that is the thing that is the transformation. That explains where we're going towards, basically. In this circumstance, there's no rearranging to be done, because where we were going was already an untransformed function. It just happened to turn out nicely for us, so there is no rearranging to be done. Y dash is already on its own, x dash is already on its own. If you then want to formalize that a bit, you might use this sort of point notation system where you say xy is being mapped to x take 1, y take 6 on 3. That's one way you could express it. And that might be where your question ends. It might just say figure out the mapping. But more likely, step 4 will come into play, which is express as a sequence of transformations, which means literally using the language of transformations. So, how do I handle this? Well, I handle this just a little bit differently to how you handle, how you might have been taught to handle this. My recommendation is to start by taking any coefficients off of the x and the y. So the reason why I recommend you start with this is because it treats it like you would for any other function. I want to build that habit early for you. So for example, if I had something like the square root of 2x minus 2, it is very common for someone to look at that and think, oh, I've got a horizontal translation of 2 to the right. You don't have that. What you do have, in fact, is a translation of 1 to the right. The reason being, you didn't take this coefficient of 2 into consideration. So whenever you handle functions, you should always make sure that the coefficients off of these values should be taken off. Right? You don't want them impacting it because it makes it very hard to figure out what was actually done to it. So for that reason, my recommendation is that you do this here. Right? You take off any coefficients that exist. Technically, this is already taken off. All I'm really doing is bringing it out to the front, but the point still stands. If this was perhaps a multiplication of 3, you'd want to take that out the front as a common factor. But okay, we've done our rearranging. Now, if you do what I'm suggesting, you need to write it in order of translation, reflection, dilation. That might be different, again, to what you've heard, where you would have heard do a dilation, reflection, translation in that order instead. We'll look at when you use what. But if you're following this circumstance here, doing this rearranging to get coefficients off of the x and y, then you do t, r, d. Now, one more thing to highlight is that it doesn't matter if you do the x first or the y first. The only thing that matters is that each individual x is done in the order TRD, and each individual y is done in the order TRD. So one possible sequence could be starting with the x and then going on to the y. You could do 1 unit in the negative x, followed by 6 in the negative y, and then finally dilation factor of a third along the y, or you could say from the x. Alternatively, you could do the y stuff first, but again, TRD. Translation of negative 6, dilation of a third, so translation of negative 6, dilation of a third, and then finally a shift left by 1, or 1 unit in the negative x direction, which is more math speak. These are the typical terminologies you should be using if you write it in an exam. This will help you get that highest possible study score, even though technically speaking, saying 1 to the left is correct. It just might not be looked on as favorably as if you had used proper terminology, which is a shame because it does take up a lot of space on your page. Okay, so when do you use DRT? Well, you would use DRT if and only if you take that point that you had. So we had x, y, and it was being moved to x take 1, y take 6 on 3, y take 6 on 3. You would only ever do DRT if and only if you expand this out. So you make sure that there are no, you don't factorize, you go the opposite direction, you expand it out. Which for us means you have x dash equals x take 1, nothing to be done there. But now y dash is equal to y on 3 minus 2. That is when you do DRT, when you expand out. So if we were to do DRT, let's start with the y first. You would do your dilation factor of a third. You could say along y. I'm going to say from x, just to change it up a bit. You could then say down by 2, or more specifically, 2. Yeah, I'm just going to say down 2, but you know, you would say 2 units in the negative y direction. And then finally, you'd have that left by 1, or more specifically, 1 unit in the negative x direction. So that's how and when you would do DRT. It's very important to understand. Only do DRT if you're going to expand things out. Do TRD if you're going to factorize. My personal recommendation is do the factorizing because it teaches better habits, but if you're going to do DRT, then that's fine as well, as long as you remember to do both. Well, as long as you remember to factorize when necessary, when you're doing actual sketching. I do have another example here, not because it's any different, but because it's the same. So I want you to understand that it doesn't matter if you go from transformed to untransformed or the other way around. Hell, it also doesn't matter if you go from transformed to another type of transform function. You still follow the exact same situation, the exact same steps. So, step 1, once again, where are we starting? Where are we going? We're starting at f and we're going to g. Untransformed to transformed. So, g is going to get our y dash and our x dash. Y is going to get the f of x. From there, again, everything that affects the y goes on the y side, everything that affects the x goes on the x side. Nothing is going on here, so you leave it as is. A bunch of stuff is going on here, so we're going to change it up. This is a shift up by 3 and a dilation factor of 2. Hence, we're going to put those on the left-hand side along with the y value itself. From there, we equate the x components to each other and the y components to each other. Here is the x component, I guess it's here. Here is the x component of g, here is the x component of f. And so we are equating those two things together. Here is the y component of g, here is the y component of f. And so we're equating those two things together. Now here's something worth highlighting again. You always rearrange for x dash and y dash. In this case, you can see it's trapped. It's not quite on its own just yet. Whereas in the previous example, if I scroll all the way back to that, it was already done, right? When we did our equation, it was already rearranged for us. In this case, we don't have that luxury. We've got to do a bit of rearranging. It is just linear, so it's not too bad. If you then want to use a point expression, then you could write it this way. And that is one possible answer, depending on what the question is actually asking you to do. As I said, it is quite likely that you'll have to write it out using the correct terminology, like the English terminology of it, rather than the mathematical one. And so you just express however you like to express it. In this case, it's already expanded through, quote unquote expanded through, so you might consider using DRT in this situation. So I've done TRD just to keep things consistent. So again, we can just sort of look at this together on the paper. So if we're doing DRT in this situation, we've got x dash equals x plus 2 and y dash equals 2y plus 3. This is already expanded since the 2 is already on the y directly. And so when you do your DRT, this would be a dilation factor of 2 from the x. This would be a translation up by 3, or 3 units in the positive y direction, and then 2 units in the positive x, or just right 2. That's a DRT way of thinking about things. As for a TRD way of thinking about things, this is when you would do your factorization. So you take the 2y plus 3, you take that common factor of 2 out the front, and fix up the plus 3 as well. Then if you do your TRD, you've now got a translation of 3 over 2 in the positive y, dilation factor of 2 along the y, or from the x, and a shift to the right by 2, or translation of 2 units to the right. So one of the issues with transformations is that there are multiple correct answers. It's a very tough thing to mark because, well, you've already seen one DRT method, one TRD method. I can think of already like maybe 3 different ways just by looking at this that you could rewrite this. Because you could do y then x then y, you could do all the y, all the x. You've got a lot of freedom with how you write these things. So just because your answer is different to the book does not necessarily mean that you got it wrong, which is what makes it really tough. This is where you need to have like a teacher or a tutor to really help you out with understanding, did I get this exactly right? Alternatively, you can literally sub in your transformation to the original function and see, do I get to that transform function? But that takes a long time, so I wouldn't necessarily recommend doing that unless you have a lot of time in your test. One other thing worth mentioning is you don't necessarily need to do what I said. You don't need to necessarily do it in the point form. You could do things by recognition, is what it's called, where it literally just means you can quite quickly see what's going on with the functions just because you know how those functions work. Like in this case here, what does it take to go from f to g? Well, we can quickly see that the only difference between f and g is a translation to the right by 2, just because we know how quadratics work. And so that's what you would say. Horizontal translation to the right by 2. So other examples can be more complicated. This is more of a set of guidelines that can help you out with doing this stuff. Start by figuring out what it takes to get to the general form of both of those functions. Recall that y transformations are independent to x, so you can do all the y then all the x, or all the x then all the y, or even interweave them if you want, but don't do that, that just makes things more complicated. And then do stuff in DRT. So, what does this look like? Well, we have a completed square quadratic and a regular quadratic. It's in its polynomial form. If we're following the guidelines that I'm recommending, start by getting things in the general form, which for a quadratic means its completed square form. So we're going to take g of x, complete the square order, and that's going to get us to this stage here. Now, we can directly compare these functions. We can see what it will take to get from f to g. Excuse me. We can see what it would take to get from f to g. Reminder, y is independent to x. So when you do things that affect the y, you don't have to worry about what's happening to the x. and doing things in DRT is more of a recommendation. The reason why is because dilations will impact your translations. Sorry, I should say dilations and reflections impact your translations. So if you do things in DR then T, your translation will maintain whatever it was when you initially started it. Either way, we're just going to compare now. So if we start with dilations, we know that F has a dilation of 3. So it's already got a dilation of 3, and we need to make it a dilation of 4. How are we going to do that? Well, we're just going to multiply by 4 over 3. When you multiply 3 by 4 over 3, the 3's will cancel out, and you'll be left with 4. So here's a divide by 3, here's a multiply by 3, you'll be left with 4. But what you will see is that everything else in the function is going to be impacted, namely the other y value, the vertical translation. You'll see that the x hasn't actually been changed at all because it's trapped inside the square. It doesn't actually get impacted. Next up, reflections. Do we need to do any? Well, if you compare f and g, you can see there's no negative signs on either the function or on the x value. These don't count, these are subtractions. You're looking for negatives either here or negatives on this value. So we can skip the reflection stuff. Next up, we're going to compare translations. So if we're getting from f to g, we want to figure out what do I got to do to this to make it look like this. And in this case, it means we need, you just want to find the difference between those two things. So whatever that difference is what you want to apply. So in this case, it turns out that if you were to add 8 on 3 to 28 on 3, you would get 12. And so that's what we're going to do. And you'll find that when you do that addition, it doesn't actually impact this 4 at the front, because that's a multiplication. When you add values at the end, it doesn't change what you did previously, as opposed to if you had done multiplication, this would change what you've done here. Anyway, add your 8 on 3, that gives you 12, and the only thing left to do is fix our horizontal translation. So if you're comparing f to g, let's see, that's where, you've got x minus 2 on f, you've got x minus 1 on g. And so what's going to take to make it look like g? Well, we want to add a 1 there. So when you add a 1 in a function, that does mean you're shifting to the left by 1. So you're going to take your x take 2 and add a 1 to it, and suddenly f is equal to g. All we're going to do from here is list what you actually did to get there. So if we go all the way to the top, we multiplied by 4 over 3, and we added 8 on 3. So that means dilated by 4 over 3 from the x. Yeah, from the x. And then we vertically translated by 8 over 3. Oh, and we also did I forgot the negative one, the x. We also shifted left by 1. And so you just write it in that order that you did it. That's pretty much it. So that's transformations. You can do it by point form, you can do it by recognition. Recognition is a lot more algebra, whereas point form is more, it's more steps, but each individual step is pretty trivial. It's never gets more complicated than linear. The only thing that gets a bit complicated at the end is which order you write things in. This one's a bit more easier to keep track of because you just do it in whatever order you did it. Whereas here you've got to make sure, do I expand, do I factorize, and if so, do I do TRD or DRT? If you're part of the community, you have access to this little cheat sheet of like all these notes that I've gone through here. You have access to those as part of the community. If you're not part of the community, drop in have a look at the chat or the description. There's a link to get you in there. Okay, there's a little cheat sheet here to tell you what each of the transformations look like in point form and in function form. And that is it for transformations. So as for where you might study this sort of stuff, this would be in the Cambridge Unit 1 and 2 books in Chapter 7 to 14. It could be in, Chapter 7 review, up until Chapter 7 review for Cambridge Unit 1 and 2, once again. And if you're doing Cambridge Chapter 3 is where this sort of stuff goes. So pretty much everything in Chapter 3. Let's see. It'll be, translation, dilation, reflection, all of that. Yeah, all of Chapter 3. that's where you can study it. And alright, that's about it from me. Have a good one.